Memory consumption is a very big topic in C, C++, and other OOP languages. In general, this consumption could be broken down into three major categories: static, stack, and dynamic. There's actually a lot more. We'll get into the delineations of other logical categories in the next slide. But for now, let's focus on static, stack, and dynamic. Static memory is allocated by linker and persists throughout the lifetime of a program. So basically, if we had a member of a class, a function, or a method, and declare them as static, that means these members of the class would be available the moment the executable starts and stay available throughout the entire run. This is because the compiler assigns them a static address in memory. They are accessible outside of the modules where they are defined. You can think of static member having a scope that is going to last throughout the lifetime of a program. The accessibility of static variables, methods, functions could be influenced by visibility rules, such as declaring them protected or private inside a class, or declaring them inside a function. We'll talk about those later on. Just remember that as soon as your program starts, these static member variables, functions, and methods come into existence until the program stops running. In the context of C and C++, you can think of a static object as constructed prior to the execution entering main and destructed once the execution finishes. A typical memory layout of a running process also includes stack, which is also known as the automatic storage. Stack is used typically for block scoped or function local variables. When a function is called, a portion of memory is reserved, and all of the variables declared in the functions are created in this space. Sometimes when you just declare a variable like integer k, this integer k is located inside the stack. So a lot of times we call them static allocation of memory. And note that this static is not the same as the memory footprint static. So the static allocation is the same as stack memory. As soon as variables and anything inside of it functions become out of scope, the stack memory used to store these variables and functions are reclaimed. As we talked about earlier, the stack memory is reclaimed by way of memory consumptions being popped off of the call stack or activation frame. There's only a limited amount of predetermined or arbitrary amount of memory in stack. Note that the stack is always reserved in a LIFO or last in first out order. The most recently reserved activation frame or block of memory is always the next block of memory to be freed. This makes it really simple to keep track of the stack. Freeing a block of the stack is nothing more than just, adjusting one pointer, aka the top pointer. So for the purpose of discussion, think of stack as some sort of scratch space for a thread of executions that is set aside when the program runs. In contrast, dynamic memory is what we call heap, which is a memory set aside for dynamic allocations. This is not stack. There is no enforced pattern to the allocations and the allocation of blocks from the heap. You can allocate a block of memory at any time and free at any time. In C, C++, we use new malloc, where new is C++ context, malloc is C context. New is also a context for Java for dynamically allocating a block of memory. Generally, there is a pool of memory reserved for dynamic memory or heap, unlike stack, which is typically tied to a thread. There are many threads at runtime. Therefore, the size of a stack is determined when a thread is created. Normally, there are many, many threads running inside a process. The size of the dynamic memory or heap is set on application startup. This size can grow as the space is needed. And this is a much, much slower process than stack memory. This is because the access pattern of stack makes it trivial to allocate and deallocate memory from it, while the heap has much more complex bookkeeping involved in an allocation or deallocation. And because heap is allocated inside an application, usually multiple threads inside a process that runs this application all have access to it. This makes heap having to worry about maintaining multiple threads or concurrency in a multi-threaded environment to be multi-threading safe, namely each allocation like new or deallocation like delete needs to be typically synchronized with all the other heap utilizations in the program. In the next slide, we're going to talk about some of the other logical compartments. In addition to stack, heap, and also static, we also have other logical compartments such as BSS, data, and text. Let me briefly describe what they are. Generally, BSS stores uninitialized global static external variables. The example is when you have, for example, integer I, or you can say char k being an array of maybe 10 elements. So these variables are stored inside the BSS region. Data region is a little different. It contains initialized static variables like integer I equals 5. This I is stored in the data section. You could also have global variables and local static variables. They're all sitting inside this data section. Text section sometimes is also referred to as code. This is what we call read-only. In computer science, a memory is broken down generally into read-only, memory, or RAM, which is read-write. Code and text sits in the read-only section of your memory block. The rest of it sits in the read and write RAM. The details associated with what each of these compartments, what they're doing, is beyond the scope of this programming class. When you take operating system, they'll probably talk about these as typical layout of a simple computer's program memory space with these compartments. The reason why we're talking about this and why this is relevant to us is by giving you an overview of how memory space is maintained and how instructions are stored in them gives you a better idea of the differences between stack and heap to help you learn memory management more efficiently. For C, C++, you don't have to memorize what gets stored in what, but just remember the major memory spaces that we discussed, because these concepts are carried over into the contemporary programming languages and they are still widely in use today.